So my name's Leo Howden. I'm a co-founder and managing director of Descycle. And I'm here to talk to you today about how we're changing an industry that's really central to some of the things that you've been hearing about over the last few days. So when I was putting my presentation together, I really wanted to make it as relevant to the audience as possible. So I'm going to tell you a few things that you probably already know, but then I'm going to tell you why they're relevant to what we're doing at Descycle. So we are a global community, connected together through a web of technology. And that technology 30 years ago would have sounded like science fiction, but now is science fact. The internet revolution has ushered in a new world, one that has empowered and connected people to an extent that it's scarcely believable how we ever lived without it. But as we're moving forward, we're breaking new ground and moving away from a physical world to a virtual world. Dropbox, OneDrive, Google Cloud have all replaced the physical with the virtual. And web-based apps, SaaS-based products, have given us everything at our fingertips in a virtual cloud. But the tether that connects that cloud to the earth is very real, and it's called a data center. Data centers are the physical manifestation of our virtual world. There are over 8,000 of these centers spread across the globe, and they have become a truly indispensable part of our infrastructure. They are so intrinsic that they're almost forgotten by the public. But as we take another leap forward in computing with generative AI and machine learning, their importance is only going to grow. Imagine adding 500,000 servers a year for AI training. Double that when adoption really takes off. The number of data centers is going to grow massively. But what makes this new wave different from the previous one is that those earlier waves were built on incremental cloud computing, and it was broadly used. It's called commodity hardware. But that model is drifting, moving in the other direction. The hardware for AI and machine learning is going to be very different. Compared to the basic cloud hardware, the equipment for AI is going to be far more complex. We're moving from what's at the top to what's at the bottom. 3 times the circuit area, 5 times the processors, 6 times the volume, and 10 times the power consumption. And these data centers must deliver higher power, more bandwidth, and expanded cooling. And the physical servers themselves have to have more connection points to create the compute environment needed to train large models. But what underpins all of this amazing technology is a simple thing: metal. Miles of copper wire and plating for electricity and heat transfer. Gold for high-speed connection. And palladium for power delivery. And this growth in data centers comes as manufacturers and cloud service providers are adopting circular supply chains and negative carbon goals as climate issues impact business practices. So as the use of these data centers continues to grow, it's going to create a problem. AI is going to be relying on technology that has a major environmental impact. Now, consumption of resources is something that is generating a lot of attention. Already, the energy cost of data centers is immense. They consume between 2 and 3% of worldwide power, and that's expected to climb to 10%. There are even predictions that the demand from data centers is going to outstrip the electricity production globally. In fact, power consumption is such a concern that the European Union is even considering placing data centers into space to be powered directly from the sun. And it's not just power consumption. Water consumption is an issue too. A large data center can consume anywhere between 1 million to 5 million gallons of water a day, enough for a small town of 10 to 50,000 people. But it's not just the consumption of resources that's going to be problematic. All of the new server boards are going to be replaced at a faster rate than they have been before. We're going to go from a refresh rate of every 5 to 7 years to every 2 years, which means increasing demand for things like AI is going to be contributing to the world's fastest growing waste stream, electronic waste. Think of all the server boards and motherboards and everything in your electronics. Globally, there's over 50 million tons of electronic waste is produced every year, and that's forecast to double in the near future. And if you want to visualize that, think of 125,000 jumbo jets stacked side by side, more jumbo jets than have ever been created. It's an environmental emergency, and AI is going to be contributing to this problem. But the thing about e-waste is that it's actually very valuable, and it's worth the effort to recycle. There's even a term for it, urban mining, turning trash into treasure. The downside, though, is that we are very bad at recycling and dealing with the pollution from the digital world. In fact, only 17% is actually recycled. The rest is left to rot in landfill or sent to underdeveloped countries, where it eventually leaches into the environment, creating yet more pollution. So that means that not only are we creating pollution from not recycling, but we're also losing large amounts of metal that we need to dig up and process again. And this itself has a huge impact on the environment. Mining metals is responsible for 4 to 7% of annual global greenhouse gas emissions. Now, what are we doing with what we're actually recycling? Well, all those server boards and motherboards, they are recycled through a highly intensive process called smelting, which is just another way to describe burning metal at high temperatures, using a process that requires significant amounts of energy and produces emissions that lead to poor human health conditions. So why is this all important? Well, it's because we live on a planet with scarce resources. Those resources are only going to get scarcer as we increase their demand. The International Energy Agency estimates that the global economy is going to need 6 times the amount of metal in 2040 than it does today in order to reach the global goal of net zero by 2050. We should be recovering those resources in what we have already used and doing it in a way that is sustainable to meet this challenge. Because we have to ask ourselves, is it really smart to be relying on new sources of metal to meet our transition to net zero when we already have so much in what we're throwing away? Now, what if we wanted to create a new way of getting these metals out that wasn't so negative to the environment? Something that didn't rely on using extreme temperatures, didn't rely on lots of energy, or didn't produce CO2 or metal emissions. Wouldn't that be a great way to recover the metals? Something that is to create something that is actually sustainable. What would it need to look like? Well, you would want to use something that was non-toxic as your base. Maybe something where the chemicals were organic, biodegradable, readily available. It would also help if they were reusable. Now, I know that that might sound like science fiction, but just as I said at the beginning of my presentation, that we're always turning science fiction into science fact, we're doing the same here at Descycle. We are implementing science fiction. We've taken over 20 years of scientific discovery and innovation in a new field of chemistry and created a catalyst for a profound change in the metals industry. Let me show you what we're doing. Our technology is based on a new class of chemistry known as deep eutectic solvents, or DES for short. DES are a unique class of chemistry that were invented right here in the UK in the early 2000s. And they are mixtures of organic, biodegradable, recyclable commodities. It's not a water-based system, which means it works very differently than current processes. Think of these as solids that, when combined together, create a liquid. Now, to visualize that, think of two slush puppies being mixed together at the cinema to make a favorite drink. So what are deep eutectic solvents? What does it mean? Let's break it down. We have the word deep, something that's intense. We have the word eutectic, which basically means something where a mixture that has a lower melting point than its constituent parts. And we have solvent, which is something that can dissolve other substances. And when you put it all together, you get DES. Powerful solvents with amazing superpowers. So to help me explain their superpowers, I'm actually going to lean on one of my all-time favorite books, The Alchemist by Paulo Coelho. And in this story, our hero's journey meanders through a series of events until he meets the alchemist, somebody who can help him turn lead into gold. Now, I'm not saying that DES is going to turn lead into gold, but its superpower is, just like in The Alchemist, one of transformation. DES can take a metal and transform it so that it's able to move into a liquid, just like a cube of sugar dissolves in a cup of coffee. So what's going on? As I said, DES are a combination of organic, biodegradable bulk commodities. They're made of things like carbon, oxygen, nitrogen, and hydrogen. Think of things like urea, which is a common fertilizer, or vitamin B4, which is used as an additive. When you combine these chemicals together, really cool things happen. The lattice energy of the system, which is what's holding everything together, drops, and these solids become a liquid. And in this liquid that we've created, it loves metal ions. It loves them so much that when we put a metal into the solution, it dissolves like the sugar cube I talked about earlier. So let me show you what I mean. If you can play the video, please. So here we're taking our solids, combining them together, and they become a liquid. And in that liquid, we place what we want to dissolve. And the metals dissolve into the solution, and then we can recover those metals. But the beauty of DES is that it's not consumed during the reaction. It's a medium through which it happens. So we can use it over and over again. It's completely recyclable. So now that we've got a new way of recycling metals using mass-produced, biodegradable, organic solvents which aren't consumed in a chemical reaction, what can we do with them? Well, it turns out quite a lot. With DES, we can selectively recover metals, which means we can tailor a process to take something out or leave something behind. We can recover a range of different metals, but crucially, without the current associated environmental impact. And that's the key here. Using DES is a cleaner way to get hold of the metals that are going to be in demand as we move to net zero. The waste that's generally thrown away is an amazing opportunity to recycle metals from one generation to the next, creating a circular economy. And it also brings in elements like traceability, which are important for supply chains. If we know where something came from, if we know what's in it, we can create a chain of custody. And with DES, we can recover that metal in an environmentally sustainable way. So that means that we don't have to rely on pollutive processes like smelting. In fact, because DES is organic, biodegradable, and works at low temperatures, the cost of construction of a plant to process electronic waste and recover this metal is an order of magnitude cheaper than a smelter. And it's an order of magnitude smaller in its footprint, which means we can create local recycling, moving away from big aggregate smelters to something that can happen at the local scale within cities transforming the way that we get our metal. Now, because DES works on e-waste, it also works on the rocks that hold the metals themselves. DES is a platform technology. We can use it in a range of industries, which opens up a whole new opportunity to make mining the metals we need to reach net zero cleaner, transparent, and more sustainable. If you want copper for electrification, we can get the copper out. If you want nickel, cobalt, manganese for electric vehicle batteries, we can get that out too. And if you want to remove toxic chemicals from contaminated sites, we can do that as well. And now looking longer term into the future, when the world doesn't want to rely on mining in the Earth, and we look to space to mine asteroids instead, we can use DES there too. Because if you're going to be using or going to be millions of miles from home, you don't want to be using something that's going to get vented into space like water, and you don't want to be using something that's going to be consumed. You need something recyclable. You're going to need something like DES. So I'll finish on that exciting thought of space exploration. Let's finish with a simple statement. For too long, we have relied on toxic chemicals and intensive consuming processes to recover the metals we need for centuries to power our industrial growth. We have now the opportunity to break that reliance and make a statement that the environment should not be paying the price for our economic development. The technology that we're developing at Descycle, using deep eutectic solvents, truly has the potential to change the way the world recovers the metal we desperately need to transition to net zero, so that we can have a cleaner, healthier world alongside a prosperous one. We shouldn't accept that it's either or. Thank you.
Good stuff. I think one of the things that makes me so excited about this is that it's been this kind of a painful progression for us over the last, decade or so, as we started to recognize that recycling isn't really working in general. And we're all separating out our trash, we're getting our cans and bottles separated from the cardboard, and almost none of it is working. And we've, really over our lifetime tried to build out recycling for the cheapest crap on earth, cardboard and plastic bottles. And what's amazing here is you're going after the most valuable stuff. And it seems like the place to start. I think that's just amazing. When you talk about the way that DES works, I guess what I think maybe it'd be helpful to just pick apart is like, how does that compare? You talked about the smelters and the incineration, but are we going to be able to get all that metal back from data centers? Are we going to get it out of phones? I mean, how much of it do you think you can really get to?
Well, with electronic waste, we can get everything.
Yeah.
So the great thing about electronic waste is that it's all native metal. The metal's right there, ready to be recycled. What we need to do is do it more sustainably. Okay. So we already know it works by putting it in a smelter. What we're saying is you don't have to do that. You can get the same output with the chemistry that we've developed.
Because a smelter is just going to literally burn everything, send most of it up the smokestack, and then leave you with a little bit of the metal. And so with DES, you get rid of the smokestack. What happens to the other stuff?
So if you take something and you incinerate it, you evaporate everything, and you put metals into the atmosphere, you burn plastics, you create toxic chemicals. What we're doing with DES is we're using our chemistry to allow us to separate the parts of the electronic waste so that they can be recycled, and the bits that we're interested in, all of the metal components, they get separated out, and then they go into our solution, and then we can physically recover that metal without touching the plastics and everything else.
Wow. And what's the scale of the market, do you have a sense of like how much metal we could recover? How much is going into electronics in the first place?
So it's the value of raw materials.
Yeah.
Makes recycling electronic waste, very, very economic. It's a $60 billion a year annual value of the contained metal. That's likely to double in the near future.
$60 billion a year of metal goes into electronics.
Yeah, exactly, and that's metal that we have to then take back out of the ground because we're putting 80% into landfill.
And how much of it's being recovered right now through with the
That's
smelter?
17% that I'm talking
17%.
Yeah.
Wow. Amazing. Folks have questions? I can keep asking questions, but if you guys have questions, they're probably better. So, yeah, over here.
Hi, thank you for the talk. Super interesting. What's the ratio of the liquid to metal you're able to pull out?
Mm-hmm. Yeah, I'm not going to say what the ratio is, but what I will say is that because it's not consumed in the reaction and it's a medium, it means that once you've put it in, you rarely have to replace it. So you constantly regenerate and reuse it, which is a complete change, 180 degrees to what normally happens. If you want to extract metals, you normally put acids. Those acids are consumed, creates carbon dioxide, and you don't have that acid anymore. With DES, it's the opposite. It's always there. It's like that cup of coffee I discussed.
Wow.
Yeah, hi. So obviously there's already a lot that's gone into landfill. Is it economic to fetch that out, or is there a plan to be able to find what's already there to recover it?
Sorry, for the electronic waste? Or? Yeah. So in landfill, I don't think we've really kind of taken a look. I think if you can get it back out of landfill and make it in a kind of environment that we're able to process, absolutely. In fact, it's probably even more valuable than what's being produced now, because back in the past, we'd use a lot more copper, a lot more gold in some of the circuit boards. So it's incredibly still valuable. We've just not looked at it from that perspective yet.
I've seen videos of kids in Southeast Asia trying to scrape the gold off of circuit boards. Yeah. And I mean, it's a nasty business to be in. Wouldn't wish that on anyone, but it's amazing to think about being able to do it in a non-toxic way. So, yeah, over here.
Hey, I want to ask if there'll be a process for detecting whether the e-waste that's going to be recycled is still operable, and if that is going to be reused, or if it'll also be recycled into raw materials.
Sorry, could you repeat that? I couldn't hear the question.
I wanted to ask if the e-waste that's going to be recycled will have a screening process before being recycled to detect whether or not it could still be reused by itself, or if it will...
There's some, I can answer that. We have a lot of problems with that right now. It's not going very well. But what's happened in some markets is they've sort of sprung up a sort of intermediary companies that are trying to intercept the e-waste, see if they can refurbish it, and then remarket it or take it to a market where it's still useful. So that's your old phones and computers and things. And I think that's starting to improve. It's not going to impress anyone, I think. At this point, it's not at a scale that's meaningful, but these guys are kind of downstream of that. So it wouldn't be what they would do, but right now you can see like cell carriers and stuff have these buyback programs and things like that, and they're trying to intercept that stuff and get it back into the market so it can live longer before it gets thrown out. But the truth is, I think there's very limited possible returns on that. By the time somebody wants to throw out a computer, there's a very small market that's going to find it useful in a lot of cases. Yeah.
So this is linked a little bit to that first question, or the question that we just had. How much processing needs to be done? Let's say, just take your average PC, for example. How much processing needs to be done before it gets to your process where you're extracting the actual core minerals? Because obviously there's the plastic, there's the rubbers, there's a whole bunch of stuff that goes with that, which you're not interested because you're interested in the valuables. So how much processing needs to be done before it gets to your stage?
Yeah, look, that's a good question. I think it'd be useful just to explain how how our technology can be adopted, because all of that disassembly of electronic waste is already happening. Like there's the groups that we're working with. We've got a joint venture with a recycler in the UK to co-locate our first plant. It's really all about integration, because groups and companies taking our electronic waste have to separate it into the different waste streams, the plastics, the glass, the components. It's already being dismantled. What we're offering is, rather than the opportunity to send it to a smelter, where they don't get paid that much money, goes into high incineration, creates pollution, and transportation of hazardous waste, we're stepping into that point and co-locating our plants with existing recyclers, so that rather than putting it into a smelter, they're recycling it on their own site, having done all the dismantling that they would have done anyway.
Yeah. Awesome. Thanks for coming out, Leo.
Great. It's been a pleasure.
Thank you, guys. No, appreciate it.